Hello, everyone. It's 3:30 here in Colorado, and it's time for an Econ seminar. Welcome to people here in the room. Welcome for the people online. It's an honor and a pleasure for me to introduce Dr. Luke Western. He received his PhD in remote sensing of volcanic ash from the University of Bristol in the UK. He then worked as a postdoc with the Atmospheric Chemistry Research Group at the University of Bristol and as a part of AGE. I tried earlier, still. Network. He worked on the inverse modeling of greenhouse gases and ozone-depleting substances to derive emissions at regional to global scale. Since 2021, he has been at NOAA's Global Monitoring Laboratory on a Marie Curie Research Fellowship to improve estimates of global emission of ozone-depleting substances and non-CO2 greenhouse gases, which is what he's going to talk about today. Before starting, I'd like to remind you, people online, that you can enter a question at any time during the talk in the space below the video, and I'll read those questions at the end of the talk. And with that, I'll leave the floor to Luke. Take it away.
Okay, thanks very much for that introduction. And is the microphone working? Is that it is? Okay, great. So thanks very much. As I said, I'm going to be talking about ozone-depleting substances today and how emissions of many ozone-depleting substances are increasing despite controls that have been imposed on their production in order to reduce emissions. So despite these controls, they're still going up. All this work is work I've been involved with in some capacity. I'm going to sort of weave through a story here, but this work has come from various organizations. So part of it when I was at University of Bristol, who was part of the A-Gauge consortium. So that's a consortium of organizations who monitor F-gases and ozone-depleting substances around the world. Some people at NOAA, so where I currently am at Global Monitoring Laboratory. And also Johannes Lauber was a big contributor to this in Forschungszentrum Jülich. Okay, so I'll start off with a bit of background. So I think most people know about ozone depletion in the stratosphere and how an ozone hole formed over the Antarctica. And this was from long-lived ozone-depleting substances. So mainly at that time it was CFCs. So CFCs are a bit of a wonder product, or they were thought to be at the time. They're non-flammable. They're very good refrigerants and things like that. So used really extensively in all sorts of applications. But then it was found that they were ozone destroying. And once this was known, there was the most successful environmental treaty ever formed was the Montreal Protocol. And under the Montreal Protocol, they aimed to phase out these ozone-depleting substances, so namely CFCs. The way they would phase them out is by phasing out their production. So no controls were placed on their emissions to the atmosphere, but it was imposed on their production. And the reason for that is that if you have a refrigerator in your house, an old fridge containing something like CFCs, and it's leaking, you're not doing anything illegal by having it. So it was, okay, we'll have a stage phase out of that. So the original idea was to phase out these CFCs, which were ozone-depleting substances, and also quite nasty greenhouse gases. They're sort of hundreds of thousands of times worse than CO2 over a 100-year time horizon. So these were replaced by something called HCFCs, which I'll talk about a bit. So HCFCs were the replacement for CFCs. They're still ozone-depleting substances, but they're probably about a tenth in terms of how bad they are for ozone. They're still pretty nasty greenhouse gases as well. They were always seen as a bit of a stopgap, and they were replaced by something called HFCs. HFCs don't deplete ozone, but they are still pretty potent greenhouse gases. And these are really the substances I'll be talking about today. So the phase out was staggered. So it was originally done for developed countries. So developed countries would phase out these substances first, and developing countries had a longer time to do this. So the global phase out of CFCs was completed in 2010. They would then transition to HCFCs, which again was a staggered phase out, should be complete about 2030 around the world. And the funding mechanism is essentially developed countries help developing countries phase them out. And then that's one of the reasons why it's been so successful. It's the only truly global environmental treaty that every country has ratified. And then, not really, it's sort of a subsidiary of the Montreal Protocol, but the phase out of HFCs, so these are ones which don't destroy ozone but are quite nasty greenhouse gases. So these are being phased out under something called the Kigali Amendment, so that's sort of in addition to the Montreal Protocol. And what's really quite interesting about that is that it's no longer an ozone-related treaty. It's purely a climate treaty. It is not, hasn't been signed up to by all countries. It's well, 147 last time I checked have signed up to it. So the US voted. I'm not sure if they're fully ratified yet, but they at least intend to join. I think maybe now they have. But late last year they were sort of a bit later, I guess, than many other developed nations in signing up. And that's to phase out these substances to about 85% of production. So that's something which is ongoing now. Okay, so that's a bit of background on the controls imposed, and again, these things are controlled on the production of these chemicals. And overall, it's been very successful, but there are a few cases where, even though this control on production is trying to limit emissions, there are especially some notable cases where emissions are actually increasing. And I'm going to go through just 3 examples. One is CFC-11, which was quite widely publicized. So one of the sort of a major ozone-depleting substance used in large quantities in the past. I'm going to talk a little bit about its direct replacement, something called HCFC-141b. And then I'm going to collectively talk about a whole host of what I'm calling minor CFCs. They're CFCs which with a much lower abundance in the atmosphere. And then finally, I'm just going to finish on a few challenges that I have and we have within the community of monitoring these things and facing the Montreal Protocol. So on the right there, a couple of figures taken from the ozone assessment that comes out every 4 years, addressing the state of the ozone recovery and gases which deplete it. So the main point I want to make really is that, okay, at the top there is in terms of CO2 equivalent emissions, the bottom is CFC-11 equivalent emissions, so people often are used to CO2 equivalent emissions, so in terms of a global warming type idea. CFC-11 emissions we talk about with sort of equivalent in terms of ozone depleting potential. So overall, the emissions of these gases, these emissions on the plot, have peaked around 1990, and they've fallen right down, especially in terms of ozone depletion. They're continuing to fall, but one thing to, even if you don't really care about the ozone layer anymore, which some people don't, even though it's still an important topic, you can think about this in a climate context, and actually, if we look at F-gases and these gases collectively, in terms of their CO2 equivalent emissions, that hasn't really changed for the last 10 years or so. So they're big contributors. And here we just have a pie chart. This is by no means all contributors to radiative forcing, but just taking the big 3 and then some of the gases that I'm talking about. In terms of radiative forcing, they're actually quite a large contributor. So larger, taken collectively, larger than something like N2O, probably 2/3 of something like methane, which often media-wise and things gets much more focus. And we are talking about these gases collectively, but that's often how we need to think about these. Lots of small things add up to something quite big. And one of the reasons as well to think about this is these gases are very long-lived. I mean, especially CFCs can have atmospheric lifetimes of 100 years or something compared to methane, which is about 30. So they stick around for a long time, and that's why even despite the fact that the emissions have really fallen, the radiative forcing from these gases is still quite high. And especially with a big thing from the last ozone assessment, so it's like the sort of sub-box in the top right-hand corner. The top one is that HFCs are now, emissions of HFCs in terms of their global warming potential have overtaken that of CFCs now. So HFCs are now quite considerably contributing to climate. So I'm going to really sort of start kicking off with these examples now. So first one was CFC-11, and this was quite a big story, especially in the ozone community. It had international attention. It was a very small box, but it was on the front page of the New York Times, for example, when it was discovered that emissions of CFC-11 were increasing despite these controls imposed on their production. And the first paper, it was Steve Monska and others at NOAA, and they saw that the atmospheric abundance wasn't dropping as quickly as we thought, and emissions were actually increasing. And this sort of, I don't want to call it a witch hunt, but there was definitely a search to find out, well, what's going on here? Why are these things increasing? Is something slightly untoward going on? And this is really where I got involved in the story, and that was doing regional emissions estimates of greenhouse gases. So I'm not going to go anywhere in this talk into technicalities of methods and things. I'm going to try to keep it quite high level. But qualitatively, what we do, this plot on the left is the triangle is a measurement site. That color is actually where the wind is coming from, or the air is coming from to make the measurement. So sort of darker colors are where we have more, the emissions will influence that measurement more. We'll get a bigger signal. And you can see when we went over northeast China, or these measurements are coming from air, which comes from northeast China, we get these big spikes in the measurement record. On the right there is just concentration measured on Jeju Island, a Korean island. And then when we're sort of looking over Japan or over the sea, that concentration is much smaller. So qualitatively, you can sort of tell that something is going on up there. Those emissions are quite high in something which otherwise should just be sitting in. Stuff like building foams is a big use of CFC11 or some old refrigeration units. So it should be low emissions sort of seeping out, where we seem to be getting these big spikes in emissions once we look over this northeast China region. So there again, you get these big pollution spikes. And then, I guess, a lot of stuff I do, you sort of put this information into a statistical framework, and then you can better quantify where these emissions are coming from and how much needs to be emitted in order to make that measurement. So then we had a paper on that, using both the Korean side and also it's a Japanese site, which is off the coast of Taiwan. So we use these two measurements to try and determine where it's coming from and how much. There's a certain range to how far you can do this for, because that sensitivity drops off the farther away you go from the measurement site. So we could only really sort of see the east of Asia, western Japan, around that area, well, and the Koreas. But these are the emissions we came up with. I mean, mine was the one on the left, and then we had 4 groups independently do this, using the same measurements, but in terms of their modeling framework, and we all basically came up with the same area. So the top is pre-Montreal Protocol phase out, and also during the years that phase out, and then 4 years after the phase out is the middle row. So that we basically see there that emissions have increased after the phase out of production. So once we stopped production, actually emissions went up, which is sort of counterintuitive when the expectation is emissions go down. And the bottom there is just a difference plot. But we all sort of indicated that they're primarily coming from Shandong province in northeastern China. And then this was, I think, 2019 we published this. And then pretty much as soon as we published it, or I think probably as we were writing it, emissions actually started to fall following the first one. And there was, I mean, admittedly, collectively in the parties to the Montreal Protocol were very proactive in this. But yeah, we saw this decrease happening sort of in 2018 into 2019. We can't say exactly when, but it seemed to be 2018, things started coming down. 2019, we were sort of almost back to where we thought things should be. And that's just the black line there showing that. So the dashed line there is trajectory of what we almost would expect to happen. The black solid line is more the path that it took. So we got this big increase in emissions. But the increase and decrease was only about 60% of what we saw globally. So globally, we quantified this. Regionally, we quantified this. So from this region in China, it accounted for about 60% of that. There's big uncertainties on all of those numbers. So even though it's 60, it could more be up to about 90%, could be much lower than that. But we don't know if that was the whole story or not. But one thing we didn't notice there, and again, sort of, I guess, qualitative evidence, but 2 substances associated with the production of CFC11, so CFC12 and carbon tetrachloride, they also weren't falling, even though we'd expect them to. And the reasons why and these elevated emissions of these gases suggested that production was also occurring in this region. And the reason for that is that if you make CFC11, you have to make CFC12 as well. It's something to do with the industrial process that you end up with both of them. So the fact that they weren't dropping as quickly as we thought suggests that they were probably making it. Carbon tetrachloride is a feedstock, so basically the ingredients you need to make CFC11 is carbon tetrachloride, and we also see a sort of bump in those emissions. But then what this was key to was suggesting that actually something illegal was happening here. So again, just emissions coming out isn't illegal. Sort of using it purposefully is, but sort of, I won't get into that. But essentially, if we think about it in terms of production, we had to sort of know that production was occurring to know that something illegal was happening. So that was the first part, there was lots of people looking at this, lots of industrial experts as well as us doing atmospheric studies. And it seemed like the most likely cause for this was the people were using CFC-11. It's used as a foam blowing agent. So basically when you have insulation foams, it's if you imagine sort of an aerosol can or something, or I don't know, fake snow. You know, there's some propellant in there, and it expands very quickly, and that's why it's used. So it was likely that people were just reverting back to it, and part of that is because it's cheap, and apparently it's just really good. That was what a lot of the experts said, that it is a really good substance. So if people thought they could do it under the radar, maybe they were. But it actually is a success story. I mean, it was one of these things that was identified. There were all sorts of projection of maybe what that could have caused in terms of delaying ozone recovery. But it seems now that we're almost back on track of where we should be. And part of that is internally, countries like China were very proactive of trying to crack down on these sorts of things. And one of the, people don't really know, and it's one of these ideas that if people are doing criminal activity, you never really know why these things would happen. I think there was a quote from one of the parties, I can't exactly what it's from, but you know, criminals are either lying or untrustworthy, so you never know. But, you know, even if people admit to it, you never know what's going on. But one of the ideas was actually as this phase-out schedule continued, people started phasing out the next generation, HCFC 141b, which is the main replacement for CFC-11s, with HFCs, the newest, more environmentally friendly alternatives. But because of cost purposes, HFCs are actually quite expensive. Rather than transitioning to a better alternative, they were just going back and getting a cheaper one, which was actually worse. So HCFC 141b is a little bit what I'm talking about next. So ignore just look at maybe one of those lines of orange and blue. The blue one, there's some peculiarities with the fact they diverge, but that's not important here. But basically what we see is that at the start, going back around 1990, developed countries started phasing away from CFCs. And what we see here is production ramped up as people were phasing away from CFCs and adopting these other substances instead. Then developed countries started phasing down their use of HCFCs for more environmentally friendly or ozone-friendly alternatives. And that's why we see there's a drop in production. Sorry, I should probably add as well, why we know these production numbers is because countries are obliged to report them to the UN, to the Montreal Protocol. So we actually have quite good data on how much of this stuff has been made. So it dropped. We then saw an increase as CFCs were being phased out, so leading up to 2010. People were transitioning over to HCFCs instead. Developing countries were phasing out CFCs, and now we're on the phase out of this generation for HFCs. So again, we're seeing a fall in production of this stuff again. I've got this little green line down the bottom, and that's feedstock use. So I said I measured carbon tetrachloride as a feedstock. So a feedstock is a chemical used to make other chemicals. Feedstocks are exempt under the Montreal Protocol because the assumption is that they're not going to be released to the atmosphere. So if you use in something like a fridge, these substances will probably end up leaking out, or they could leak out, or your car air conditioning unit, or foam blowing as well. It gradually leaks out over time. So they're assumed to be released to the atmosphere. Feedstocks aren't. They're assumed to be fully converted or chemically converted into a different chemical. So you can use HCFC 141b to make other chemicals. Its usage is pretty stagnant over time. So we can sort of ignore that part for now. And what we noticed in the record, so there's two global networks which measure these things. We have A-Gauge, which is a consortium of organizations, and NOAA here, which have sites around the world. And it was really subtle, but basically, so this is abundance in the atmosphere at different sort of regions of the atmosphere. But if you just, the black line is it's been going up and up and up. And we basically were just sort of getting to the tipping point. So this is the growth rate in the atmosphere at the bottom. We're sort of tipping to about 0, maybe just starting to decline. So we basically thought we were getting to the point of emissions or concentrations in the atmosphere were no longer increasing, possibly starting to decrease. And very, very subtly, they started to grow again over the last couple of years. So something we noticed, and I guess what I can do is then you can convert those things into emissions. What emissions would you need to cause that small change? This is a very bold plot here, but this is using the two different networks, sort of the yellow shading, the blue line. But what we saw is that, much like the production, we saw an increase in emissions. The emissions dropped as production dropped. Emissions increased again as production increased. And they started to fall again as production started to fall again. But rather than continue to fall, since about 2017, we saw an uptick in emissions of this gas. We wouldn't expect a one-to-one correlation in terms of the size of the peaks and the troughs, and that's because, say you put this stuff into a refrigerator. Well, HCFC 141b is one of the big uses of it is it's used in foams, but actually in the insulation of refrigerator foams. It's a really big use for it. So when you put these things in something like a foam or in any substance, it's going to take a long time to leak out. So it sort of smooths those peaks and troughs over time. But still, it's something we hadn't seen before is this later increase as production decreases, apart from the case of CFC11. And what was really sort of, I guess, research type alarm bells were ringing is that if we put CFC emissions on here, we saw this big decline in global CFC emissions basically at the same time as we started seeing this uptick in HCFC 141b. So I guess the big question we were worried about then was, well, if people have stopped using CFC 11, and we could see that in the record, but if people just started using HCFC 141b instead, which wasn't completely phased out, but it was being phased out, and people shouldn't be reverting back to using that. But it turned out it was a bit more complicated than that. And like I said, it's emissions of these gases happen at various stages in the life cycle of the gas. So this stuff is made, you'll get some leakages, say, in the factory process of this stuff being made. And then if you're putting it into something like in a fridge, you're going to get some leakage when you're putting it in to the production of that. This stuff's sitting in your house, so if you have something like these gases in a fridge, it's going to be gradually leaking out over time, or an air conditioning unit. And then you're also going to get leakage during disposal. So depending on how you dispose of these things, so if you had, say, insulation within a fridge, if you take it to a landfill and it gets crushed, you're suddenly going to get a big burst of this gas coming out because you're crushing these foams which contain it, you get a bit of plume. So, and it's quite a complicated process to look at, and I think, if you're really into fridges, it's quite interesting. and things like, for example, in the US, there's really interesting when you look at things like how old is a fridge, what's the life cycle of a fridge, and for example, the US has a big thing for beer fridges. So actually, there's lots of very old fridges in the US because people will have them in their kitchen for the life cycle of a fridge, and then they might move them down to their garage or somewhere and keep them for another 10 years, purely for beer or snacks. And then that sort of changes the dynamics. And then when people try to validate these atmospheric-based studies, we talk to experts in the field, and there's a lot that goes into it, and what countries are using what when. So this is another thing that could be going on. Like I said, that you get a delay in these emissions. So we had to look a bit closer at that. And one of the ways of doing that was looking regionally. So can we do a sort of study we did for CFC 11, for HCFC 141b around the world? We can use all. So one of the things with the way that these networks have been built is most of them have been built as background sites, so basically far from any polluting sources, and that's sort of historical reasons of when you're quantifying global emissions, that's really what you want. But when we quantify regional emissions, so say at sort of US state level scale or country level scales, we need them close to polluting sources, not too close, but close enough to them. And so we use the sites we could use, so there's quite a dense network in the US. In Europe, it's quite good. East Asia, there's a certain amount we could use. There are more sites that are on this map, little pink dot, but there are some more sites, but we can only use one for this. Down in Tasmania, we can sort of see some of the urban areas of Australia. So we were limited of where we could look, but we thought maybe by looking regionally, we can get some idea about the patterns of these emissions in different parts of the world, which might tell us something about the life cycle of these. Of this gas in particular. So here, so basically the blue line that turns orange, that's emissions of this gas in Europe. So sort of northwest Europe really, but within Europe there's big uncertainty in early years because we didn't really have many measurements, and they're probably a bit larger than they should be, those error bars there. But what we can see is that emissions were high when usage was high, when production of this stuff was high. It was being used a lot, put into stuff like refrigerators. And then it's fallen down to very low levels with very good timing of when it was phased out in Europe. And one of the reasons for that is under EU and European law, and similar in other non-EU countries, it requires the destruction of HCFCs if they're contained in things like appliance foams. So in many countries around the world, if you have something like an air conditioning unit or a fridge to get rid of, they'll sort of suck out the refrigerant and destroy it. But actually, if it's contained in foams, that's not the case everywhere. But Europe is one of the places that they'll take the foams out and they'll destroy those foams in a way that destroys the HCFCs within them. The green line there is the US, or the contiguous US. So this is an estimate by the EPA, so it's not based on atmospheric measurements, it's done in an accountancy method. But what they see there is that you have this peak in emissions around the same time as in Europe. This first peak when it's being used quite extensively. You get a bit of a drop-off as production decline, but then they attribute then this large peak sort of in the mid-2010s down to the destruction of fridges. So basically, if people are throwing out these fridges in places like landfill, you're going to get these big plumes coming out. And the US doesn't have any requirement to destroy this gas when it's disposed of. They encourage it, but it's not legally required. It might be in California, maybe. I don't know. But anyway, it's generally not required through the US. We don't have long-term records, atmospheric records in the US, and that's because there's contamination issues. But the little black and purple line there are a few years that we do have of atmospheric measurement records, which we can derive emissions from. So there is a bit of a mismatch there. It'd be really nice to see if we could see it if it would actually follow those peaks. But they're still much higher, say, than in Europe that had similar usage of these sorts of gases. So what this says, in some ways, is, well, at least there's a possibility. Someone can independently say there might be a delay in these emissions because of the disposal of something like old refrigerators. We could look at Australia. They have similar laws to the US in terms of they encourage destruction, but they don't require it. So the two lines are just different methods of an accountancy method of calculating this, or based on atmospheric measurements. The much less smooth one is based on atmospheric measurements. But yeah, there is no sort of large second peak here. So it doesn't really tell us that much, actually, about what is going on in these countries. But there's no sort of obvious huge peak coming from Australia, say. We could look in somewhere like East Asia. So accountancy methods, that's the orange shaded line there on the left plot. So these bottom-up or accountancy type methods suggest actually the emissions should be increasing in China, and that's again attributed to people landfilling things like old fridges. The atmospheric measurement-based estimates, so that's the blue line, are quite noisy, but they sort of follow, suggest that could be happening. They peak. So the accountancy methods suggest that we'll see a peak around 2026, around that sort of time. Basically, as the life cycle of these things like fridges start to come to an end. It's not great, it's pretty noisy. There's not great agreement there, but essentially it could be happening. This could be an explanation of what's going on. And on the right, some other European countries, East Asian countries. So South Korea, it's just the western part of Japan. So they actually have laws there for destroying these things as well. They're quite low levels. I mean, North Korea is, who knows? But South Korea is possibly, it seems fairly flat, maybe peaked at some point. But again, the uncertainties are pretty large on that to draw any real conclusions. But what this study sort of suggests is that even though we looked into this really in earnest because it could have been another sort of CFC11 type scandal that people were using something they shouldn't be, it seems that at least in part these things can be explained by what we call the bank. So the quantity of this gas which has been installed in appliances and is sitting there. So it's been produced in the past, but it's still waiting to be emitted. But we don't really have a sufficient regional measurement network to fully quantify whether this is going on around the world. So we can see that there are some increases possibly around the world. We can probably attribute about 30% of that. So around 30% of the global increase we can attribute to these emissions we can quantify regionally. But we really think that, it could be quite likely that this is purely just coming from the general life cycle of things like fridges, which is a big deal because again, the whole Montreal Protocol is restricting production, which people often assume is directly correlated with emissions. But actually, what we might be seeing is delay 15 years after. And when we think about things like net zero targets, actually, if we stop making something now, maybe those emissions are going to come out in 10, 20 years' time. And especially when these things have such high global warming potentials, we really have to think about these things when we're thinking about stuff like net zero. Of, okay, if we're stopping producing this now, we need to make sure we dispose of these things in a and not even just dispose of them because they leak out during the life cycle as well. So we need to think about these things going forward. And what we don't know, and a big question now as well, is this going to happen with other substances? So the HFCs, which have been brought in, they're quite early on in their life cycle. Are we going to start seeing these being emitted in higher quantities in 10, 15, 20 years' time? But it was sort of an open question. This was published last year. And we couldn't really have any firm conclusions of what was going on, but just exploring these and saying there are multiple explanations. And the only thing really we could exclude is feedstock usage, sort of definitively. It would require sort of slightly crazy numbers for that to happen. But now as I'm going to move on to talking about feedstocks and the use of some of these chemicals in the production of other chemicals. So I'm talking about a whole host of CFCs now, which I'm guessing most people have probably never heard of. So CFC 13, CFC 112A, 113A, 114A, 115. So quite long names, and these are very low abundance CFCs. So CFCs were used widely around the world. It was mainly CFC 11, CFC 12, CFC 113 with the three big ones that were used in all sorts of things, refrigeration, air conditioning units, solvents, aerosol sprays. These had much more specialist usage, so sort of extreme temperature refrigeration, some solvents, some feedstock use, things like that. So their global abundance mean global abundance is about less than 10 parts per trillion in the atmosphere. The major ones are orders of magnitude higher than that, so 50 to 500. So these are quite minor in the atmosphere. But what's quite interesting about these is their abundance has all been going up since 2010, so since the phase out of CFCs. And even though each of them are quite low abundance collectively, they account for a fair amount. But what's sort of interesting is that there's basically no known uses for them. So there were in the past, but some of these things you can explain through economic reasons why people might transition back. But even when they were used, there were very few uses. There aren't really banks of these things. A lot of them were used as stuff like solvents. So they were used at the time and they would just be immediately released to the atmosphere. So it was a bit of a mystery of why these things were increasing in the atmosphere when there's no sort of logical use for them, when they can be easily replaced by other stuff. Again, we can take these concentrations and turn them into emissions. So on the left there is in terms of CFC 11 equivalent emissions, so in terms of their ozone depleting potential. On the right is in terms of their CO2 equivalent emissions over a 100-year time span. And so some of these are much worse, greenhouse gases than others, some are much worse, ozone depleting substances than others. But really, again, since 2010, we've seen this big shoot up in emissions, which 2010 was the phase out date globally for these CFCs. And again, if we, this is interesting for ozone. These are primarily ozone depleting substances, but if we want to think these in terms of a climate context, in 2020, just these five gases together, the CO2 equivalent emissions are about the same as a country like Switzerland. So people often, when people who study these things talk about these in terms of climate impact, people tend to, shy away from it a little bit sometimes. But actually, if Switzerland suddenly became net zero, it would be a huge deal. But actually just by, these gases which seem to have absolutely no feasible use, if we manage to reduce these emissions to zero levels, then it's equivalent to, say somewhere like Switzerland or something like that, just completely getting rid of their CO2 equivalent emissions. So one of the things was trying to work out, well, okay, if these things have no real dispersive use, so use that might be released to the atmosphere, how else might they be used? One of those is actually in the production of HFCs. So HFCs were seen as these more ozone-friendly alternatives, second generation after CFCs. And this is the extent of my atmospheric chemistry here, just chemistry. So we start with some feedstock, so PCE here. And you use that to make HFC 125. But you end up with lots of byproducts when you make HFC 125. And 3 of these CFCs I'm talking about are some of the byproducts you'll get, particularly CFC 115. The reason we know this is, one, people who work in industry have sort of told us, is one of these things you can't really just cite in a paper, but they say you do end up with some amount of this. It's just down to the production process. And they're encouraged to destroy these byproducts, but if they're not destroying these byproducts properly, then maybe they're making their way into these chemicals. HFC 125 is a big air conditioning substance, so it's used very extensively in things like car air conditioning units, portable air conditioning units, things like that. So we sort of anecdotally know that this is happening because in one of the measurement stations, there was an air conditioning unit which used HFC 125. It had a leak, and as well as measuring huge concentrations of HFC 125, we also measured huge concentrations of CFC 115. So we sort of know that this is not being destroyed properly in the process. It's contaminating the HFC 125 and being put into air conditioning units. If that's then leaking out of air conditioning units, it's going to make its way into the atmosphere, and we're going to measure it. So these are HFCs, which are non-ozone depleting substances, and it seems as though we're probably getting some contamination from these ozone depleting substances within them. Another gas is HFC 134A. That's the most widely used HFC, and that's not used as a feedstock or as a byproduct, but 2 of these gases, CFC 114A and 113A, intermediate gases in that production. So you start with something called CFC 113, you react it a load of times and get to HFC 134A. Some of those reactions pass through 114A and 113A. So if you have, say, a leaky production process, or again, some of these things aren't fully converted during that industrial process into the final target substance, and you can end up with contamination or leakage of these gases as we go. So that's what some of these gases are probably coming from. If we look, so this is a really busy plot, I'm sorry. But if we look there, the blue shaded bit there is production of HFC 125 and HFC 134A in developing countries specifically. And we can see that this has really increased since 2010, where production in developed countries has stayed pretty constant. And this timing is fairly similar to the increase in these CFCs. It's qualitatively quite similar. So we think maybe these gases are just linked to the production of other chemicals. And again, these processes are allowed under the Montreal Protocol. So the assumption that you take a gas, you fully convert it into something else, that they're allowed under the Montreal Protocol. And that's a way that you can legally still make and have CFCs in the production process. I'll just briefly say that we do actually get a turnaround in CFC 115. And I spoke to someone who's an expert in air conditioning units, and they said that possibly is a COVID-related thing, that if this stuff is making it into refrigeration units, apparently there were production issues, something to do with compressor pumps. And so there weren't as many air conditioning units sold over the COVID period, so she seemed to suggest that was not surprising, if it is linked somehow to air conditioning. But the other substances didn't see this drop. So maybe that, which could suggest that maybe that's something to do with leakage during production processes as opposed to being put into that final product. But it's speculation. But there is a change with CFC 115 compared to the other things. Again, this is production of one substance and emissions of the other, so these things aren't directly related. So there's a lot of information on here again, but basically, so the yellow, the blue, and the orange gases are the ones I just spoke about. They seem like they're likely linked to HFC production. CFC 113A is also used to make lots of other target chemicals, so HFOs, which I haven't mentioned, but they're under the Kigali Amendment. That's what people are switching to away from HFC, so that HFCs are quite bad greenhouse gases, but fine for ozone. HFOs are okay for both. So basically why that's in there is because if CFC 113A is being released to the atmosphere from chemical processes, then it means that a long time in the future, maybe we're going to still see emissions of CFCs unless these processes are tightened. So pesticides, TFA, and other things. But the 2 other ones, the blue one and the green one here, so CFC 13 and CFC 112A, are still a bit of a mystery. We don't really know where they're coming from. CFC 13, there's some speculative things you could say. So It's also a byproduct of CFC11 production, but we don't see a fall in that like we did of CFC11. So if people were illegally producing CFC11, perhaps we would see CFC13, but like I said, we don't see a drop there. When you try to destroy CFCs, so in some of these cleanup type procedures where you take CFCs and you destroy them, you can actually produce CFC13 as a byproduct in small quantities. But we don't have any information on how widely it's used. It's using a particular method called plasma arc destruction, but there's no real public information on that sort of thing. So it's sort of speculation. And CFC1 and 2A, really, we have no idea. It's just a bit of a mystery of where that's coming from. But I think the take-home message is that these emissions are likely coming from processes allowed under the Montreal Protocol. So these are things that have been made exceptions. And again, there is sort of a slight success story here that the reasons why we can see these things happening is so that right at the start we had that plot of CFC emissions really falling down low. And actually emissions of these things are coming to such low levels now that we can start seeing these minor usage and things like feedstock uses, which were otherwise quite negligible in terms of CFC emissions. So it's not good that these things are happening, but it's reassuring to know that we can see these things happening because usage has come to such low levels. So first set of conclusions before I come on to just a couple of challenges we're facing. Quite short, but emissions of many ozone-depleting substances are increasing, and this is particularly long-lived ozone-depleting substances which are controlled under the Montreal Protocol. We see some different drivers from different usage or different scenarios. So one was CFC11, and that was because it was unreported production. It was production that shouldn't have been happening under the Montreal Protocol. We've also seen its replacement, HCFC141b. That's delayed emissions from the banks. So the banks are where it's been stored. So we're seeing a delayed emission after it's been put into its appliances. And finally, a whole host of other CFCs, which we're seeing likely during the production of other chemicals, and other chemicals which are seen as being more environmentally or ozone-friendly, even though this sort of fairly nasty substances are being released during their production process. So I'm just a couple of slides now. I'm going to talk a little about a couple of challenges. Oops, I need to stop doing that. Challenges from my point of view when it comes to quantifying emissions mainly. And one which I've already touched on is a measurement network. So this is all the sites around the world which make regular long-term measurements of ozone-depleting substances, and crucially, who make their data freely available. So there are some more sites. Someone like China has quite a good network, but it's not freely available data. And the shading here is essentially where we're sensitive to emissions. So which regions can we quantitatively quantify emissions around the world? So somewhere like Europe, we have quite good coverage. We can quantify them quite well there. North America, sort of in the east of East Asia, so Japan, Korea, the east of China. But there's huge ways of the world here that we don't have any sensitivity to. We don't really know what's going on. So India is a big country that's quite important. Russia. South America, we don't really know at all what's going on. The Middle East is possibly a big region. West Africa, for another region, which would be interesting. We don't really know what's going on. So even though globally we tend to have quite a good handle on these things, in certain regions we have quite a good handle of what's going on. But we definitely can't jigsaw puzzle together the world and look at emissions. Another just slides here are emissions of ozone-depleting substances which are not controlled under the Montreal Protocol. So a lot of these are very short-lived substances, so substances that have an atmospheric lifetime on average less than about 6 months. They have both natural and anthropogenic sources, and this is something that they're becoming increasingly important. So in terms of their contribution to ozone depletion, as these long-lived substances are falling in the atmosphere, their abundance is falling in the atmosphere, emissions of lots of these gases are increasing, and they're becoming increasingly important in terms of ozone depletion. This is just from the ozone assessment again, a plot made. So PCE is one of them, the top one. It is falling in the atmosphere, and the emissions are falling, but both chloroform and dichloromethane have really shot up in the last 10 years. Chloroform has actually fallen a little bit the last couple of years again, but these are substances which are ozone-depleting substances and are not controlled under the Montreal Protocol. And we've done some work, it was mainly led by Minda Ann, who's at MIT, but he had a paper, was it 2 years ago, in looking at dichloromethane, and basically the entire change in global emissions could be explained by emissions from China. And we have a paper currently in review looking at chloroform, which is basically saying the same thing, that we don't necessarily know that all global changes are due to China. Stuff might be going on elsewhere in the world and trading off, but it seems like most of these changes could be controlled by those changes in emissions in China. And one of the reasons, which I know people here are much more knowledgeable about than me, but one of the reasons why this is really important is because of the Asian monsoon and rapid transport up to the stratosphere or to high altitude. So some conclusions now. It's sort of a success story, I guess, that the emissions of these ozone-depleting substances have fallen to such low levels now that things that would otherwise be in the noise, so for example, when we saw these emissions happening of CFC11, we can now detect them, and that's really a success story of the Montreal Protocol, that emissions are generally falling. For most substances, they have fallen, but we are still seeing increases of some of these emissions. We can quantify these quite well on a global scale, but regionally, we sometimes struggle, and that's down to, is mainly down to our coverage of the measurement network. Even if we are reducing emissions of these things in general and controlling production in order to reduce emissions, so what we call the bank, so these which are still in appliances, can cause an increase in emissions sort of later down the road once they, say for example, when these things are destroyed. And it's something that, especially when we think in a climate context, stuff like net zero doesn't really often think about the release of F gases from banks. And then another thing is that we also are seeing some of these gases released during industrial processes, for example, producing HFCs and HFOs, which are ozone-friendly alternatives. But despite that, it seems like there may be some ozone depletion as associated with their production. Even if the gases are ozone-friendly, the production process might have some ozone-depleting cost to them. And things like HFOs are expected to be used far into the future. And I've only just touched on a few things here. There are other ozone-depleting substances and long-lived greenhouse gases which are increasing the atmosphere. So halons, two of those are going up in the atmosphere or have weird intermittent increases. There's plenty of HCFCs which are probably tied to industrial processes which are either increasing or not falling. HFCs, so the later ones, there's some peculiar things going on. And like I said, with VSLS and these short-lived substances are shooting up as well. So still a lot of work to do. It's not a done deal. Yeah, thank you very much for listening.
Thanks, Luke. We're 10, 12 minutes for questions from the room and online. Oh, sorry. I was blind and I
Really interesting talk, Luke. I'm curious, so for the HFC production for like the new fridges and air conditioning units and things of that nature, is there a way to figure out how many like CFCs or like how many things should be a byproduct of that and limit it? Or is there like, does it vary widely depending on, the process?
I guess it's two-pronged, is whether I can work it out or whether people producing can work it out. So in terms of what I know, and I guess what we know as atmospheric scientists, we can get rough estimates from experts on emission rates or leakage rates during this production, and they vary quite widely. So they were always thought to be quite low, so maybe sort of 1% of that byproduct, or 1% of the intermediates would release. I think the latest IPCC report puts the range, I think the sort of 95% confidence interval was something from 0.1 to 20. So they've really expanded that leakage rate. But I think they know industrially. So if you look at things like patents of these production processes, then they will quote different production methods and because they're aiming to produce as much of this target chemical as possible, so they want to reduce that as much as they can. So they have an idea of how they can react to these things, and part of that's a cost. I understand that you can make things in a more cheap way and it's slightly dirtier, or you can make it more expensively, but you get diminishing returns, I think, the more you put in, is my understanding. So yeah, they probably know, and I think they have quite good scrubbing methods to get rid of these things, but again, there's costs. Or even things like sometimes you have these scrubbing methods to get rid of some of these byproducts, but I think they need to be serviced or cleaned every so often. So during that period, they'll just turn them off, for example, and they'll clean them and service them. So even if these things may be just intermittent, we know that sort of thing goes on, that they'll just switch it off for a bit. So perhaps it's just in these situations. So people know. I don't.
We have another question here.
Thank you. It was a very interesting talk. So I'm still puzzled by this ground network, global network, AGAGE, and I'm not sure how the USA one is called, and the lack of that type of measurements in the southern hemisphere.
Mm-hmm.
So are you aware of any initiative or action to overcome that, or is there no? Because these measurements are not required from the Montreal Protocol, apparently.
Yeah, so there is a push, both from, currently there's an EU initiative which is being backed by UNEP of trying to expand the network. It wasn't very much money in the grand scheme of things. It was more a feasibility study looking at where would it be most useful to place these things and trying to pool expertise. I was a little bit involved with that, talking about site placement and where would be good places to put them. So it's on people's radar. There are two different types ways you can, and that was all surface measurement sites. There are some aircraft measurement campaigns and things like that, but in terms of, that was long-term sort of permanent sites, and they're either flask samples where people are just filling flasks, shipping them back to, for example, in Boulder and measuring them. Some of them are in-situ stations where they're measuring online. So there is some intention to expand to the Maldives and Bangladesh, but there's not long-term funding for it. It's a feasibility study, basically, for a few years. South America, not that I know of at all. So there's, it's not happening, but stuff is being talked about.
Yeah.
Yeah.
Okay.
One more question from the room.
Thank you, Luke, for the nice talk. You have been using this word feedstock repeatedly. Could you comment on more specifically what feedstock, or specific to refrigerator industry, or there's more, or regionally, are all the feedstocks everywhere is equal, or some particular region that the feedstock is more impactful? So some examples of the leading.
Sure. So feedstocks, I mean, many of these gases are used as feedstock. I spoke about a few. One thing I haven't spoken about at all is carbon tetrachloride, for example. That's been a mystery for years. Emissions of carbon tetrachloride is a big feedstock. It's used to produce lots of other chemicals. Same as chloroform, actually, is quite widely used as well. But carbon tetrachloride has been, under UNEP and Multilateral Fund and people, there's been a lot of effort of trying to determine how much feedstock is being produced, how it's being used. So that was traditionally used to make CFCs. I think it's still now used to make HFCs and some other substances. A lot of that happens in China. They're a big producer. India produces a lot of things for feedstock, but it's even in the US that happens. So I think like Kentucky, for example, is a big industrial manufacturer of certain ones. So China is the hub, for sure. I mean, they have a huge economy and they really dominate this sort of industry. But it's done around the world. Lots of these gases are used as feedstocks. So, I mean, sometimes people conflate as well feedstocks, byproducts, and intermediates. They're all just different stages of that production. Are they produced intentionally to make another process? Are they converted along the way, or are they the end product that's not wanted? But for something like the ones which are phased out, they should only be being used as feedstocks now if they're produced. Did that sort of answer the question? Or I mean, I don't. The big question is I don't know fully where they're made, and part of that is I have production data there, and under it's the Multilateral Fund and under UNEP, when they report this data, we're not allowed to see it disaggregated. We have to see it aggregated in some way, and that's for if you're the sole producer, if you're a company and you're the sole producer of some substance, you don't want your competitors, or if there's 2 or 3 of you, you don't want your competitors to work out how much you're making. So we can't get that production data down on, say, a country. I think we have to have it at least aggregated as something like developed or developing. So I don't know what it is. I only know anecdotally from talking to experts.
Okay, we have a question from Becky from online. Thanks for this really fascinating talk. With regards to the feedstock emissions and additional unuseful CFCs, is it possible to constrain their emission as byproducts by comparing their mixing ratios to regional observations where HFCs are elevated?
Yeah, likely. This is nothing we've done, but there's a question there. We don't fully know when these things are emitted during what process. So, for example, if these things were only being emitted during the production process of HFCs, it would be hard to isolate the mixing ratios of, okay, let's take something like HFC 125. If it was only being produced during the production process and leaking at that point, so for example, they just weren't destroying them properly when they were separating these gases, it would be hard to compare because HFC 125 is also used in loads of homes, cars, things like that. So without having a good handle on where these CFCs are being emitted, it's difficult to know. I'm sure you could do it by, if you had a smokestack and you stuck a measurement device in that smokestack, you'd be able to do it for sure. But in terms of the sort of sensitive, like I said, we have quite a sparse network. We're quite far from polluting sources. We just see sort of a bulk of these gases coming along. So we could probably tell something. You know, you can look at tracer correlations and stuff like that. And there are quite a few groups who do stuff like that. But yeah, I'm skeptical of how much you could really nail it down without knowing where these things are released.
Okay. Well, thanks. Some compliments from Anonymous. Very good. That's exactly good timing. Thanks, everybody, for coming. Thanks for the folks online. And thank you, Luke, one more time.